It goes to the gateway. It will not find the address of the peer device. It will directly request the MAC of the gateway. The gateway will respond accordingly. So if the data crosses network segments, actually, the data will go to the gateway. It's here to help you forward. The same goes for the return packet. If the PC is now accessing across network segments, it goes to request the MAC of the gateway. When it requests, in local ARP cache, the MAC corresponding to the IP of the gateway will also be cached, forwarding across network segments in the future. I will directly encapsulate the MAC of the gateway, forwarded as the destination MAC. That is, when the PC is accessing across network segments, the broadcast gateway will give it a unicast reply. For cross-network communication, it directly finds the gateway. When communicating on the same network segment, it will directly find the peer device. So everyone should know the importance of the gateway by now. Now you may not have a good understanding of the gateway. Later when we start talking about routing, gradually everyone will have a deeper understanding of it. ARP request for cross-network communication. Gateway. ARP request for communication. On the same network segment. The question is directly on the other party's device. Because it is the same network segment, so it can be directly accessed by ARP broadcast. The other party can reply, because it involves a data encapsulation problem. So ARP is very critical. In fact, we sometimes refer to ARP. There is another thing. Gratuitous ARP. It has another name. Gratuitous ARP. Let me show you. For example, this is PC1 and PC2. Let me modify the IP address of PC1 just now. Change it to 1.1.1.3. 24-bit mask. Let's make another mark here in the message. Wait for it to send a new message from below. Let's take a look. I am making a modification now. You see I didn't ping. Just change the address. The following packets are captured. It will also send data packets if the address is changed. Send 3 gratuitous ARP packets. This report also has some characteristics. Let's move it up. We open this message. The characteristic of this message is that when it is in 3-layer encapsulation, it is also an ARP. But it's just that this ARP is special. Its sender IP is itself. Target IP is also itself. Equivalent to. It configures an IP address for the interface. This interface only needs to be configured with IP by default. We'll send out packets. Make an ARP request. Request is. The destination IP is the same as the MAC address of the device. Now this is 1.1.1.3. The reason why we still have to request 1.1.1.3 is to do a duplicate address detection. This is what it does. The role of gratuitous ARP is duplicate address detection. I ask you a question. If the PC sends a data packet now, destination IP is itself. Target IP is also itself. Now the peer has received. For example, PC1 sends a data packet to PC2. PC1 is configured with an address of 1.1.1.1. PC2 is also 1.1.1.1. After PC1 is configured, outbound packets PC2 received need to reply to PC1. In the same way, for the current device, it received an ARP request, should give a reply. We just configured 1.1.1.3. So it will reply 1.1.1.3. So in theory, if in an environment, if your configured IP address conflicts, Then you will receive a reply from a person with exactly the same name as yours. If you don't get a response like this, it means you have no conflict. So, it is used for duplicate address detection. So how does it work? After an interface is assigned an IP address, gratuitous ARP. So whether we configure it manually or automatically issued IP, it will also send. You will learn DHCP later. Dynamic Host Configuration Protocol. In the whole environment, this IP is unique, because as long as there is no conflict, no device will reply you. If there is a device to reply you, just to prove it's the same as your name, you need to change your name. When data forwarding is performed as a whole, it is not acceptable for two devices to have the same name. Let's move on to the next question. This problem is a little more complicated. Let's add a few devices now. Add a router. Then add two PCs. What we want to do is an extension function in ARP. Proxy ARP. We first make a connection to them. Relatively speaking, it starts up pretty fast. Let's refresh it to open it. We also turn on the device. After opening, we are going to make a configuration. Then, before configuring, first of all, we need to plan the addresses for them. I took it to the drawing board. We plan the address. What we do today is not cross-broadband. We are doing the same network segment. Suppose the IP address of the PC on the left is 192.168.1.100. Sometimes you may find you forgot some configuration. For example, if you forgot to configure the gateway, suppose the IP address of the PC on the right is 192.168.0.100. 23-bit mask. Actually, for ARP proxy, when you refer to static routing in the future, point out the interface. It will also have some relationship with. Only, nobody uses that thing like that anymore. For now, it is not very common that the host does not have a gateway. Although this feature is very useful, can solve the corresponding problems. But in fact, we are now configured to do. I hardly ever use this feature much. Let's take a look at what it can do. On the left is 192.168.1.100. On the right is 192.168.0.100. Let's also configure the interface on the right. Suppose the interface on the right side of the router is 192.168.0.254. The interface on the left is 192.168.1.254. They are both 24-bit masks. This is the respective gateway representing the PC. But we don't configure the gateway for a few days. If we access across network segments, in fact, the gateway is to be configured. Let's configure them. First, think about a question. For this scene, are the two PCs on the same network segment? PC2 is 192.168.1.100. 23-bit mask. PC3 is 192.168.0.100. 23-bit mask. Now for PC2. 192.168.1.100. The mask is 23 bits. The network bit representing it is 23 bits. The last 9 bits are host bits.